Thank you. Yeah, my talk is going to be evaluating the influence of precipitation, temperature, and soil moisture on upper Colorado River Basin streamflow and drought. I have a number of colleagues who have been helping me with this project. This is a beginning of a 2-year project, and we also have a number of water resource manager partners who are giving us input and collaborating with us on this project. So we're just starting out. This is the first question we're asking. We're trying to take a look at the role of cool season precipitation, spring and summer temperatures, and antecedent soil moisture. That is the soil moisture in the fall before the runoff, particularly addressing low flows in the Colorado River Basin. So the basin we're looking at up here is the upper Colorado River Basin. I'll be talking about Lee's Ferry, which is the main gauge here for the entire basin, and looking at those hydroclimatic variables over that part of the basin. So the first part of what I'll talk about is an examination of specific droughts, and then I'll talk about identifying and quantifying contributions of temperature and soil moisture on Colorado River flow. The data I'm using mostly is the gridded prism data for total monthly precipitation and average monthly temperature. I'm using modeled soil moisture storage from the McCabe and Wallach water balance model. The analysis period is 1906 to 2012, and mostly what I'll be talking about are comparisons based on these different variables converted to percentiles. For the particular variables, I'll be talking about October through April total precipitation for the cool season precipitation, 3 different intervals for temperature, March through May, and March through July, and then October or November soil moisture. Oh, and also for the flow, I'm using natural estimated flows for the Colorado River at Lee's Ferry. So we're looking first at the major droughts in the Colorado River Basin based on streamflow at Lee's Ferry. This is the naturalized flow record, and we're defining drought as below average flows broken by no more than 1 year of above average flow. So the brown bars are showing the intervals of drought that I'll be talking about: 1930s, 1950s, 59 to 69, some years in the 70s, late 80s to 90s, and since 2000. So this is just a comparison of the different hydroclimatic variables that were averaged over these different periods of drought. So the colors of the bars are indicating the drought periods based on the definition I just showed you. And these are percentile values. So if you look at the water year flow for all those different droughts, we see that the averaged over those drought periods, the flows are all below the 40th percentile. If we look at the cool season precipitation, the values are more variable. The 1950s was the driest drought, and the last 2 droughts, including the most recent one, was the wettest in terms of the cool season precipitation. If you look at the temperature variables, April, March through May, and March through July, you can really see that these last 2 droughts were the warmest droughts. The 1930s was also fairly warm relative to the 1950s, 70s, and I guess it was the 60s drought. And then if we look at soil moisture, the first 2 droughts were lowest in terms of soil moisture. The 1970s was the wettest, and then the last 2 droughts were more intermediate with regard to soil moisture. These are looking at a few of these droughts individually year by year, so 1930s, 1950s, 2000s. The individual years, there's a bar for each year, a set of bars for each year. The purple bar is the water year flow, the green is the cool season precipitation, the blue is the April temperature, and the orange is soil moisture. So the first thing you can look at, if you recognize the major iconic droughts for these periods, it's 1934, 1954, 2002 are all showing very low streamflow, very low precipitation, high temperatures, and low soil moisture. So that's not really a surprise. There's a lot of things to look at in this kind of diagram, but one thing that we started to look at that we thought was interesting was years like 1933, when you have relatively high flow compared to the precipitation. So the blue bar or the purple bar is the water year flow, and the precipitation is green. And then we have years like 2004 on the bottom here, where you have fairly high cool season precipitation, that's at the 50th percentile, but very low stream flow. And in those years, it looks like the temperature and or the soil moisture is playing a role in mediating the effect of precipitation. So what I wanted to do was to look at, to compare the water year stream flow and the cool season precipitation, and just see if we could tease out some differences there. So those are the 2 time series, water year flow, October through April precipitation. They go up and down together, but there are some years where there are differences. So I took the differences of those two series, and that's plotted out here, water year minus the precipitation. This is the 1 standard deviation of values, so looking at those values beyond 1 standard deviation. The blue are the years where flow is greater relative to precipitation, and the blue bars, and then these pink bars are years where the flow is less relative to precipitation. You can see sort of clusters of the blue years here and clusters of the orange years here where the flow is less effective, or the precipitation is less effective relative to flow. And if we look at those years, the blue years and those pink or orange years, and average those together, these are the values for the hydroclimatic variables. So where flow is greater than precipitation, there's the flow. The median, these are percentile values, so it's above the median for flow, below for precipitation. Temperatures are all relatively cool, and November soil moisture is just a bit above the median. In contrast, for these years where flow is less than precipitation, the temperatures are relatively high, and the soil moisture is slightly below the median. So if you remember this pattern here, we had more of these blue years here and more of the orange years here, suggesting that maybe temperature is playing a role here, as well as in these values. If we look at the trend in the March to July temperature, we do in fact see this trend, which is not surprising, suggesting that maybe our warming, partially due to the anthropogenic effects, is maybe having an effect on the efficiency of precipitation and contributing to stream flow. So for the second part of the study, so far anyway, we're looking at quantifying the contribution of temperature and antecedent soil moisture and annual flow. So I used a stepwise regression, and the pool of predictors was the cool season precipitation, the 3 different variables for temperature, and October, November soil moisture. And this is the model that came out. It had 3 steps and explaining about 75% of the variance, so not explaining a quarter still, but not surprising, the cool season precipitation accounted for about 66% of the variance. March through July temperature accounted for about 8%, and November soil moisture for about 2%. So really, those 2 variables are not contributing very much, but I wanted to see if in particular years they were more important. So this is on the top, at least for flow, the gauge values. This is the precipitation-only model, so the estimates of stream flow only based on precipitation. And then down here, the green line is on top, is the model with precipitation plus temperature. So you can see there's some little differences. But what I did was to take a look at the improvement when we add precipitation, or when we add temperature to the precipitation-only model, and that's plotted here. So this is stream flow, the high flow years, the low flow years in terciles, and then on the top here, the red values are the years where the addition of temperature to the precipitation model improved the fit, and the gray is where it didn't improve the fit, it worsened it. So it's a little hard to say there, but if we throw up the drought intervals, you can see that, particularly at the end of the record, the addition of temperature seems to improve the fit of this model. If we look at the model where we add the soil moisture to the precipitation and temperature model, the same kind of graphic, these red values are the years where the addition of soil moisture to precipitation and temperature improved the model fit. Again, throwing up those drought periods. In this case, it looks like the addition of soil moisture might actually improve the fit in those wetter years. So this is just looking at the stream flow, the water stream flow for Lee's Ferry, and these are the top 10 years for the model fit with the temperature and precipitation. So these are the best fit years. And you can see that the best fit year was a very, very wet year. The second best was a very dry year, but overall we see maybe it's a mix of wet and dry years in the top 10. If we look at the Colorado River flow model adding soil moisture, we see that instead of a different story, we see that soil moisture is really offering the best fit in the very wettest years. So if we look at the full-time series here, this is best fit to worst fit for the temperature and precipitation model. There's the first 10 years. You can see, well, maybe it's improving the dry years, although it's a little hard to say. Down here, this is the addition of soil moisture to the model. There are those really, really wet years. There's also some years that are relatively wet that are on the worst end of the fit. In the middle here are the dry years, which don't seem to be affected too much by that addition of soil moisture to this model. So to summarize, the major low-flow years, not surprisingly, are characterized by really low precipitation, high temperatures, and low antecedent soil moisture. In years where less flow, or where there's less flow relative to winter precipitation, high temperatures may be a factor, and vice versa. And these types of years, where temperature seems to be maybe influencing the efficiency of precipitation, are more prevalent. We're seeing a trend in the warmer temperatures. While cool season precipitation explains most of the variance in the streamflow, temperatures may contribute in low-flow years. I'm not sure that we can really say that, but soil moisture may influence flows in the very, very wettest of years. And as I said, this is the first step of this project. We met with our reclamation colleagues last week, and we were talking about, well, maybe there's a better way to, a better metric for looking at antecedent moisture conditions in terms of its importance for streamflow. So we're discussing that. We're going to do this analysis for 3 of the major subbasins in the Colorado River Basin. And then what we're going to try to do is reconstruct these metrics using tree rings to see if there's different combinations of soil moisture, temperature, and cool season precipitation that contribute to different droughts over the past 400 or 500 years. And then the last part of the project actually has to do with looking at those different sort of flavors of drought and contributions in the paleo record, and then looking in the models and the projections to see if we can find analogs in the future. So that's all I have. I think I have a minute or two to answer some questions if anybody has any. Thank you.
We have time for questions. Yes.
It seems that the antecedent soil moisture is going to be affected by the intensity of the monsoon season. So you end up with more summer rainfall going into the pre-season. That's a really hard thing to get a handle on.
Yeah, one of the suggestions from reclamation and also some other hydrologists that have worked on this area is to look at conditions further into the preceding summer, and maybe using a metric like PDSI. That's, the soil moisture is, it's modeled soil moisture. It's not perfect. We've looked at a couple different soil moisture models, but maybe taking a longer look at that antecedent period.
Any other question?